Okay, this is the lesson that was taught in class on Tuesday, November 3rd, for those of you that missed it. What we're going to be looking at in this lecture is how to look at a dot structure and determine what shape it is as a three-dimensional molecule. We draw dot structures as flat drawings on a piece of paper, but most structures are not flat. Most of them are three-dimensional, and we're going to figure out how to determine what that actual three-dimensional geometry is. So you need this blank chart. We're going to be filling it in as we go, and we're also going to be looking at this simulation that shows us what molecules look like and lets us rotate them around. Okay? So back to our chart, let's talk about what these different columns represent. So first we have the number of electron domains. An electron domain can be one of two things. It can be a covalent bond, or it could be a lone pair on the central atom. And we're only focusing on what's on the central atom, not the outer atoms. So of our number of electron domains, we're going to look at how many are bonding domains, meaning how many are shared in a single, double, or triple bond. And then we're also going to look at the non-bonding domains, which would be the lone pairs that are not shared between the atoms. Okay? And from those things, we're going to determine the electron domain geometry and the molecular geometry. And the molecular geometry is the most important part because it actually tells us what shape the true molecule is. And then we're also going to assign the bond angle, which is the internal angle between the bonds that's based on that geometry. Okay? So we're going to start out with two electron domains. So let's go back to our simulation. Here you can see we have the central atom. It has two single bonds around it. It has no lone pairs. Okay? So it's showing us down here our electron domain geometry is linear. These electrons within the bond want to get as far away from each other as they can. They repel each other. So they're going to get 180 degrees apart and form a linear molecule. And because we don't have any lone pairs, our molecular geometry is also linear, and our bond angle, you can see here, is 180 degrees. So if we go back to our chart, we're going to fill in, we have two bonds, no lone pairs, we have a linear molecule, and a linear molecular geometry with bond angles of 180 degrees. Okay? Now, when we look at these molecules, they could be two single bonds, they could also be two double bonds, it could be a single bond and a triple bond. It doesn't matter what type of bond they are. What matters is how many there are. Okay? All right, now let's take a look at the next two rows that have three electron domains. So that means we could have three bonds and no lone pairs, or two bonds and one lone pair. Okay, so we still have a total of three groups of electrons. It's just that some will be bonds, some will be lone pairs, and that's going to affect the molecular geometry. So now we want to add another bond. Okay, so you can see we have 1, 2, 3 bonds, no lone pairs on the central atom. These three bonds want to get as far away from each other as they can, so they're going to be at 120 degrees. Okay, so you can see it looks like a triangle, and if we rotate it and look at it from the side, it's a flat triangle. So we call that trigonal planar. Trigonal because it looks like a triangle, planar because it's all flat in the same plane. Okay, you can see it's a flat molecule with our bond angles all being 120 degrees. So we'll go back to our chart. We call this trigonal planar. And because there are no lone pairs, that is also the molecular geometry, with the bond angles of 120 degrees. Okay? Now, if we change one of the bonds to a lone pair, okay, so let's see what that looks like. So we're going to take away a bond, we're going to make it a lone pair. Okay, so here's our molecule. So here's the central atom. We have 1, 2 bonds. We have 1 lone pair. So there's still 3 groups of electrons, okay, but now one of them is a lone pair. So our actual molecular geometry is now bent. So you can see it looks like a bent structure right there. Okay. Now the bond angle in the model says it's 120, but if we look at some real molecules that have this geometry, okay, so this is sulfur dioxide, and you can see it has 2 bonds and 1 lone pair. The bond angle is actually slightly less than 120, and that's because the lone pair repels the electrons in that bond, and it actually pushes those bonds slightly closer to each other to make the bond angle slightly less than 120. So if we have 2 bonds, 1 lone pair, it's still a trigonal planar electron domain geometry because it's still 3 groups of electrons. But now it is a bent structure, and our bond angle is slightly less than 120 degrees. Okay? All right, now let's look at the next group. We have 4 groups of electrons, 4 electron domains. So that means we could have 4 bonds and no lone pairs. We could have 3 bonds and 1 lone pair, or 2 bonds and 2 lone pairs. Okay, so let's look at our simulation and see what these would be. Okay, back to our models, take away that lone pair. We want 4 bonds and no lone pairs. So you can see this shape, all those bonds are evenly distributed around the central atom, okay, and we call that geometry tetrahedral. And basically what that means is if this were to be a closed-in 4-sided shape, it would be a tetrahedron, and the bonds would point to the corners of the tetrahedron. Okay, so no matter which way you turn it, all of those angles are 109.5. They're all equally spaced out around the central atom. So here we have tetrahedral, tetrahedral, and our bond angle 109.5 degrees. Okay? Okay, now if we replace a bond with a lone pair, so take off a bond, add a lone pair, you can see that now our structure looks like a pyramid, okay, and we call it trigonal pyramidal because our 3 bonds are in the shape of a pyramid. They're pointing down, and our lone pair is up on top. Okay, so we would have a pyramid here, and just like before, if we were to look at a real molecule with this shape, you can see our bond angles are a little less than 109. Okay, they're actually about 108, 107.8. So we could go back to our chart. Our electron domain geometry is still 4 groups, so this part is still tetrahedral. But now we have trigonal pyramidal. And our bond angle is less than 109.5 degrees. Okay? Okay, and then our next one, back to our model, take off a bond, add another lone pair. Okay, so you can see the 4 groups are still evenly spread out around that central atom, but this time we have our molecule is bent. Okay, so we have 2 different types of bent molecules, one with 4 groups and one with 3 groups. And if we look at our real molecule, water is a bent structure. It is the most common example of bent, and you can see our geometry here, or our bond angle, is less than 109.5. It's actually about 105. All right, so back here, let's put in tetrahedral. This time it's bent and less than 109.5 degrees. Okay? Okay, our next group of electrons, there will be 5 of them. Okay, so let's take a look at what that means. So we could have 5 bonds and no lone pairs, 4 bonds, 1 lone pair, 3 bonds, 2 lone pairs, or 2 bonds and 3 lone pairs. So we have 4 different molecular geometries for our 5 groups of electrons. So here we go to our geometry here. We want to go back to our models. take off our lone pairs. Now we want to have 5 bonds. Okay, so let's see if I can flip this around so you can see what it looks like. Okay, so when we have 5 bonds, what we have here is called trigonal bipyramidal. Okay, so you can see we have a triangle in the middle, okay, and there is a pyramid on the top and a pyramid on the bottom, and they both have a triangular base. Okay, that's called trigonal bipyramidal. And we have 2 different bond angles. Okay, so our bond angles here, as you can see, are 90 degrees. But if we look at the molecule from the top, the 3 that are in the middle are 120 degrees from each other. Okay, so we have 2 different bond angles. So let's come back over here. So in our electron domain geometry, it's going to be trigonal bipyramidal. Our molecular geometry is the same because we have no lone pairs. So trigonal bipyramidal. Ooh, that's not a very good Y. Okay, and then our bond angles are 90 degrees and 120 degrees. Okay. Now if we go back and we replace one of our bonds with our lone pair, okay, so we're going to take off a bond, we're going to add a lone pair. All right, so you can see that our lone pair goes in the middle. Okay, this is called the equatorial position. If you think of this as being the Earth, then those 3 bonds that stick out in the middle, those are like the equator. Okay, so we put our lone pair in the equatorial position. So no matter which way we turn it, it's always going to be in the same place with the other 2 that are sticking out to the side. And the reason is, when we look at it from the top, if you remember, those bond angles were 120. So that lone pair is going to want as much space as it can get. So it's going to go out to the side where it has 120 degrees rather than being in the axial position, which is up and down, like the axis of the Earth, where it would only have 90 degrees. And here you can see that our geometry, our molecular geometry, is called seesaw. If we turn it on its side, let's see if we can get it to turn on its side. Here we go. So now it looks like a seesaw. It would rock back and forth. Okay, so that's the molecular geometry. So let's fill in what we have here. So electron domain geometry is still trigonal bipyramidal. And now our molecular geometry is seesaw. And our bond angles will be slightly less than 90 and 120 degrees. Just like before, those bond angles are going to squeeze in just a little bit. Okay? Okay, so now let's go back and put 2 lone pairs. So take off a bond, add another lone pair. And you can see that our lone pairs, again, are in the equatorial position. They're sticking out to the side here. So what we end up with is a T-shaped molecule. So same trigonal bipyramidal, but this time we have T-shaped. Okay, and our same bond angles, less than 90 and 120. Okay, and then the last one in our 5, if we take off a bond and add another lone pair, now all 3 lone pairs are in the equatorial position. And all that leaves us with our 2 bonds in a straight line. So this one is also called linear, but it's linear with 3 lone pairs. Okay, so let's go back here. So still trigonal bipyramidal. But now we have linear, which makes the bond angle 180 degrees. It's in a straight line, okay? All right, I'm out of time on this video. I'll have to make a second video to finish up our 6 groups of electrons, so take a look at that second video and we'll finish filling out our chart.